Okay, so now we can start. Now we will be basically dealing with conservation laws. In particular, energy and momentum, and maybe even angular momentum. Now, first let's discuss what do we actually mean by a conservation law. We already have one example, the conservation of charge. We said that del rho by del t plus the divergence of J is equal to 0. So if we can identify such quantities as rho and J, then we can say that the corresponding thing is conserved. Here, rho J is the flow of rho of charge. Rho is the amount of charge. We say that charge is conserved. Or if we can just integrate this equation over a volume, then we can just say that d by dt times the integral of rho over a volume. This should be equal to minus the integral of J over a surface. And again, this just tells me that whatever rho dV corresponds to, it is conserved. It just tells me that if the integral of rho over a given volume is decreasing, then it is basically flowing out of the surface. So if we can somehow obtain one or the other form, an equation in this form, we will get a conservation law. Now let's start with the energy. Now we already know the energy of particles. It's point particles. Let's call them their energy, mechanical energy. And the rate of change of the mechanical energy of our particles is what we call the power. And the power is basically F dot V. Well, F is the force density, the force per unit volume of our system of charges, of particles. Well, we integrated over our volume. So this is the power. In general, for a point object, if there is a force acting on a point object, the power of that force is F dot V. Is it positive or negative? It should be positive. So the force density, so what I'm imagining here is I have this continuous charge density, charge distribution. The charges are moving around. So you can think of, they also have some mass in practice. We never talked about the mass, but all the charges we know, they carry mass. So they have some kinetic energy. And so here we are talking about the rate of change of this kinetic energy. It will be basically due to the force acting on our charge distribution. So if I just imagine some small volume of my distribution of particles, they will feel a force per unit volume given by small f. And that small volume is basically moving with some velocity v at that instant. So the total power on my system, delivered to my system, is just the integral of F times V over all of my volume. Now the force density, we just said that it is nothing but rho times E plus J cross B. Well, just for simplicity, I will assume everything in vacuum. That V, dV. But you see, J is nothing but rho times V. So it is perpendicular to V. So that the B term doesn't deliver any power. Well, that's basically the fact that the B field doesn't do any work. So this is equal to rho times E times V. Well, now what I would like to do is just eliminate any dependence on my particles on the right-hand side. I would like to express the right-hand side only in terms of the E and the B fields. And then convert it to either the total time derivative of a volume integral or some kind of a surface integral. Let's start with rho. I know what rho is. I can express it in terms of the electric field. Rho is nothing but 1 over 4 pi times the divergence of E. Sorry, I will not go along that path. Now, rho times V is my J. Now I can eliminate J in favor of the E and B fields, because I know that curl of B is equal to 4 pi over C times J plus 1 over C times dE by dt. Or J is equal to C over 4 pi curl of B minus 1 over C dE by dt. So that tells me that the rate of change of the mechanical energy is equal to C over 4 pi curl of B dot E minus 1 over 4 pi dE by dt dot E dV. Or d by dt of the mechanical energy plus 1 over 8 pi times the integral of E squared over the volume. This is the second term. This is equal to C over 4 pi curl of B dot E integrated over my volume. Well, this term is already familiar, the energy stored in the electric field. So at least I identified the energy stored in the electric field. Now I need to simplify this one further. I need to write it either as the total time derivative or as something integrated over a surface. Now let me try to simplify it a bit. This is equal to EI epsilon ijk del over del xj bk. I just wrote everything in terms of the components. Well, this is del over del xj of epsilon ijk ei bk. This is a divergence. Minus, but of course they are not equal, minus epsilon ijk bk del over del xj ei. Now let's go back and try to express them in terms of some kind of in terms of my vector notation. This is the first term is nothing but minus the divergence of E cross B. Because that thing in parentheses, that is E cross B, the J component with a minus sign, and I'm taking its derivative with respect to xj. Now let's look at the second term. Let me also write it in terms of the vectors. This is bk. Well, this derivative over there is nothing but minus the curl of E, the k component. So did I do any minus sign mistake? K moves to the front and I and J, they exchange. So there's a minus sign. Or curl of B that E, this is equal to minus the divergence of E cross B plus B dot curl of E. Well, I know what curl of E is. Plus B dot minus dV by dt. 1 over C. Well, let's all put it back to here. times the volume integral of this thing, which is minus the divergence of E cross B, plus or minus 1 over 4 pi dV B dot dB by dt. Well, let me just move all of the terms to the left-hand side. So I will get d by dt, the mechanical energy, plus 1 over 8 pi E squared dV, plus 1 over 8 pi B squared dV. So this is the energy stored in the B field, plus C over 4 pi, the surface integral of E cross B. Now let me write the surface integral as dA. This is equal to 0 for any surface, any volume. Or I can also write this as, no, okay, this is it. So I see, this is the mechanical energy of my particles due to their motion, their kinetic energy. This is the energy stored in the electric field. This is the energy stored in the magnetic field. And since this is a conservation law, any change, no, the parenthesis closes here. Any change in my total energy is due to this flow of E cross B. So that term is my energy flow. And we give it a name, C over 4 pi, E cross B is defined as S, or the Poynting vector. So it is the flow of energy. This is what we call the Poynting vector. So now we know that electromagnetic fields, they do conserve energy if we keep in mind the energy we take into consideration the energy due to the electric and magnetic fields. So you can just imagine the surface goes to infinity, for example. If the surface goes to infinity, then the E and the B fields at infinity, they are 0. We don't have that term. So the mechanical energy plus the total energy stored in the electric field plus the total energy stored in the magnetic field, it is conserved. It doesn't change in time. So we have energy conservation. Now let's look at momentum conservation. Well, that was kind of more problematic for us because if we just imagine these 2 point charges moving in some velocities, not parallel aligned with each other, in that case the forces will definitely not be action-reaction pairs. So the momentum of these particles will not be conserved. So we have to somehow, if we want momentum conservation, we have to assign some momentum to the electromagnetic field. So let's look at that. Well, our strategy will be basically the same. We will start with mechanical momentum. So we know that this is changing. If this is changing, it is due to the forces acting on my particles, and the total force acting on my system will be F integrated over my volume V, which I can write as rho E plus J cross F, J cross B, integrated over my volume V. Now next I will just eliminate this rho and J, try to identify some total time derivatives and also some surface integrals. That's what I will do. Now let's start with, we already know rho. Rho is 1 over 4 pi divergence of E multiply with E. We know J. Well, J, we had already solved it over here. J is this one. cross B, integrate over the volume. Now at least we have one time derivative over there. So let me rewrite this dV. Let me take 1 over 4 pi out also. 1 over 4 pi integrated over the volume, E times the divergence of E plus no, here I have a J over C. But it doesn't make any difference in this derivation. The only difference is here rho times V is, no, okay. So it's J over C, it doesn't make any derivation because V doesn't contribute. Now here it will contribute, there's this 1 over C. So it will cancel this C. We have the 4 pi is out, the curl of B, cross product with B. And we have minus 1 over 4 pi C dE by dt curl of B. Let me look at the last term first. And let me see if I can convert it to some kind of a total time derivative. So I have the volume integral dE by dt. No, there's no 4 pi, sorry. 4 pi is out of the parentheses. dE by dt cross B. This will be dV, d by dt of E cross B. Yeah, it would be too simple if it was like this. So we have to subtract what we have added. This is E cross dB by dt. But I can replace dB by dt by the curl of the electric field. So this is equal to d by dt. Okay, I have the total time derivative of something, a volume integral, plus the volume integral of E cross curl of E times C. Because remember, curl of E is just minus 1 over C d5 dB by dt. So let's go back. The curl of E is minus dB by dt, 1 over C. This is the Lenz rule, that minus. This is equal to 1 over 4 pi dV E gradient of divergence of E plus the curl of B cross B minus, right? Well, there is a minus 1 over C over there, so there is a C cancelled with this one, E cross curl of E minus 1 over 4 pi C times the integral over the volume of the total time derivative of E cross B. Or let me write it in a different form, d by dt of the mechanical momentum, this is the momentum of the moving charges, plus 1 over c squared dv times s, my pointing vector. Remember, pointing vector was c over 4 pi times E cross B. So here I have 1 over 4 pi c E cross B. So it's basically the same vector up to this constant 1 over c squared. This is equal to 1 over 4 pi E times the divergence of E plus or minus the curl of E plus, no, B. No, this is not the curl, this is E. E cross the curl of E. Plus or minus B cross the curl of B. Well, this looks quite symmetrical, at least the second line. The first term is E, the second term is the first term with E replaced by B. So if the first term was also so symmetrical, it would just look nice. So let's add it. Well, divergence of B is 0. So that second term is 0. So we just added it to have some symmetrical expression. Nothing more. Well, first let's look at this one. The identification of this pointing vector as the momentum of our magnetic field, electromagnetic field. Well, it shouldn't really come as a surprise, but it's actually the momentum, if you just remember from mechanics. So if you have a point charge, point object, point mass, as it's moving with some velocity v, then some combination that is moving with velocity v, we call the momentum. Well, for a point mass, it has some energy located at its position. So we can also think of, for a point mass, the momentum is nothing but the flow of energy, also for a point mass. But pointing vector is the flow of energy for an electromagnetic system, fields. So in that sense, the appearance of the pointing vector as the momentum of our system, up to that 1/c² factor, is not really a surprise, because S basically describes the flow of energy, which we call the momentum. Now, if we can simplify the second bit, write it as some kind of a divergence, then we would be done. On the right-hand side, I have a volume integral. Because if I can write it as some kind of a divergence, either I can say that, okay, if in a region the total energy is changing, it is flow through the surface, or I can say that I can just set the surface at infinity, and at infinity there are no E or B fields, and hence that second term will just be 0 when the volume is infinite. So I get the mechanical energy plus the mechanical momentum plus the momentum of my system, of my electromagnetic field, is conserved. Now, how can we write that term as a divergence? Well, you see, all of those terms have kind of a derivatives. Now, let me take that term. E times the divergence of E plus B times the divergence of B plus, now this is E, curl of E cross E plus the curl of B cross B. And let me take its I component. I will try to show that this can be written as a divergence. So let's see, the I component is, okay, EI del J EJ. Now let me just take only the electric field piece, rather than writing it all along. Instead of taking all this term, let me look at this one. The I component, because whatever expression I obtain for this one, I can just write it for the other two terms by just replacing E with B. So this is EI del J EJ plus epsilon IJK curl of E J component EK. This is equal to EI del J EJ plus epsilon IJK. This is epsilon JLM day LEM EK. Well, just notation, this del I just use it for the derivative with respect to xi. So this is equal to EI del J EJ plus or minus epsilon JIK epsilon JLM del LEM. This derivative is acting only on EM, EK. Now I will just multiply this, and that product is nothing but Kronecker delta IL, Kronecker delta KM, minus Kronecker delta IM, Kronecker delta KL. This is equal to EI del J EJ minus del I EK, multiply with EK, plus del K EI EK. Do you agree? And just 2 more lines and we will be done. This is equal to, let's say, EI del KEK. Well, J is a dummy index, so I just renamed it. Minus 1 over 2 del I EK squared plus EK del KEI. You see, the first term and the last term I can just sum them. It's nothing but the derivative of the product EI EK. The first term and the last term.
What happened in the first term from R to K?
From J to K. Well, J is a dummy index. I'm summing over J, so I can just change its name. So that's what I did in the first term. Instead of J, I changed its name, and now I'm calling it K. K is also a dummy index.
I can understand that if we're not using K in other terms.
Well, you see, we are not using K in the same term as a dummy index. I'm using K as a dummy index in another term that is added here. I mean, the only thing I did, I could just say, instead of J, I could have just used K to start with. I mean, you see, here I already used this dummy index J here and the dummy index J over here. In different terms, I can use the same dummy indices. It's just like you have 2 sums. You can carry the sum separately or sum the corresponding terms and sum everything. Minus 1 over 2 del I EK squared this is equal to del J EI EJ. I go back to the dummy index J. 1 over 2 del I EK squared. This is equal to del J EI EJ minus 1 over 2 Kronecker delta IJ EK squared. Now let me call all of this thing as Tij. Let me also call it E because there's only the electric field there. I can just repeat the same thing, everything is exactly the same for the B. So this whole thing the I component is del J Tije plus Tijb, where this Tije is equal to Ej minus 1 over 2 Kronecker delta Ij Ek squared. Tijb is equal to Eij minus 1 over 2 Kronecker delta Ij Bk squared. Now this sum, I will just use Tij. This is called the energy momentum tensor. Now let's first look at the conservation of momentum. You see, we had this equality. This whole thing. Now, let me just define this with an additional 1 over 4 pi. In fact, with even a minus sign. You see, this time derivative is equal to minus del J Tij, now the I component of over the volume. Now that is a divergence integrated over a volume. I can just convert it to a surface integral. This is equal to minus Tij Nj ds. Nj, n being my normal direction to my surface. So you see, this here I have 3 conservation laws, not just one, for each component of the momentum. Each component of momentum should be conserved. But you see, the x component of the momentum can be flowing in the y direction. That's basically what this Tij is. It describes the flow of the I component of momentum in the j direction. Well, you see, it cannot be diagonalized in general. Given an E and a B field, of course, you can diagonalize it. You can find some coordinates, but it won't be general. And if you diagonalize the right-hand side, the left-hand side will not be diagonal. You see, the left-hand side is kind of the diagonal in the sense that it's the component of a vector. If you mix the components, you will be mixing the components on the left-hand side also. Well, I mean, in general, I don't think you can do it. For particular cases, you might be able to do it. Now, just think about a wave. A wave on a string, for example. It is moving in this direction. But the particles, they are moving up and down. The linear momentum, let's say at this point, the linear momentum of the string is in this direction, but that momentum is flowing horizontally. Although the momentum of the string is in the vertical direction, the flow of momentum is in the horizontal direction. So this is basically exactly the same phenomenon over here. In waves, the flow of momentum need not be in the direction of the momentum. So this is what that Tij describes.
Time derivative for S.
Yes? You can basically do the same thing for the angular momentum. The angular momentum will also be conserved. And it will be conserved because there will be an angular momentum of the fields. And the angular momentum of the electromagnetic field, so what should it be? You see, L is R cross P for a point particle. Now, for the electromagnetic fields, P is not just localized at a given point, it's just over all of the field. We can talk about the momentum, linear momentum density of the field, but the linear momentum density of the field is just nothing but our Poynting vector. So this is S over C squared is the linear momentum density of my field. Multiply it with R, integrate over the volume. This is the angular momentum of the electromagnetic radiation.
Shouldn't there be a minus sign between 1 over C squared
And
if we set the surface to infinity,
mhm.
the right answer will be 0,
Okay.
which means that they should be negative to each other.
No. You see, if you can send the surface to infinity, it will just tell me that the total momentum stored in the electromagnetic fields and the mechanical momentum of the particles, the sum will be conserved. So at least the problem of this not having actual reaction pairs isn't really a problem, because in that example we didn't take into account the linear momentum of the electromagnetic fields.
So this angular momentum doesn't seem to have anything to do with polarization.
Well, we will see. We still have 2 weeks left where we can study light. We will see that light, for example, polarized in a given way, it has angular momentum. Now, another thing to pay attention to is that if you look at this S, if you want to have S, you have to have both E and B fields. If in electrostatics, for example, where you don't have B fields, you don't have a linear momentum. Or in systems where you don't have an electric field, like most of the time we consider these infinite wires which were neutral, carrying current, there are no electric fields. So there's no momentum in our electromagnetic field, and no angular momentum. So if you want to have linear momentum or angular momentum of our field, we have to have both of them. Let's look at one case. If they are parallel, again, you don't have any linear momentum, you don't have any angular momentum. They don't have to, they should both exist and they shouldn't be parallel to each other.
They don't have to be changing.
Hmm?
They don't have to be changing.
Not really. You see, pointing vector has no time derivative. As long as you have an electric field, as long as you have a magnetic field, and you don't have any, and they are not parallel to each other, you get the pointing vector, which is nothing but the linear momentum in your electromagnetic field, up to that factor 1/c². If they are constant, well, they are constant. Let's look at that example. Let's assume we have a solenoid. Which carries a current I running around. So we know that inside there are some B fields in this direction. And B is equal to magnitude is 1/c I times n. This is my solenoid. So this is I, B is out of the screen. Let's imagine we put inside this solenoid a cylinder with a uniform surface charge density sigma. Well, this will create an electric field pointing outward. And the magnitude of this electric field will be, let's say it has a radius A, sigma times 2 pi A divided by S. Or let's see, E dot ds should be equal to Q enclosed. I just assume a cylindrical Gaussian surface. So that E dot 2 pi S times H will be equal to sigma times 2 pi A times H. Right? No, I have 4 pi Q enclosed. Yeah. No, that's 4 pi. So these 2 pi's will cancel and h's will cancel. So electric field will be sigma A, 4 pi sigma A over S. What's the Poynting vector? So let me just use, this is my S hat vector. The Z hat is outside. And let me call this one, this is my phi hat. What is E cross B? C over 4 pi. The magnitude is 4 pi sigma A over S. B has a magnitude 1 over C I times N. What is the direction of E cross B? E is outside, B is towards you, minus phi hat. Sigma A I N over S, the minus sign phi hat. So the linear momentum is basically circling around the central axis. Phi hat is counterclockwise. You see, this we define as the Z. Phi hat is counterclockwise. Okay, E is outside in the S hat direction, B is towards you, so it's in this direction. At that point at the bottom. So it's in the minus phi hat direction. Let's calculate the angular momentum per unit length. I mean, the total angular momentum will be infinite because it's an infinite system, but we can talk about the angular momentum per unit length. Now, the angular momentum per unit length in the electromagnetic field, this is R cross S dV. First of all, what is the direction? Yeah, let's just write this. R cross S is S in the S hat direction plus Z in the Z hat direction. This is R. My S is minus sigma A I N over S in the phi hat direction. So what is the S hat cross phi hat? S hat cross phi hat is just Z hat. So this is minus sigma A I N. In the Z hat direction, this is the first term, plus minus sigma A I N over S times Z. Z hat cross phi hat. Well, at that point, let's look. Z hat is towards you, phi hat is in this direction, it's in the minus S hat direction. So this is minus sigma A I N. In the Z hat direction, the volume per unit length this L is not the magnitude of the angular momentum, it's the length. Let me call it L, small. The integral of the volume will be just pi b squared minus a squared. This is A, this is B. This is the first term. The second term, what's the integral? It's 0. But to see that, I can write this volume integral as a surface integral over the sphere, over a cylinder, and then integrate over the radius of this cylinder also. But when I integrate over the surface of the cylinder, S is just constant, S hat is changing. When I integrate around the circumference, S hat is constantly changing. The integral of S hat will just give me 0. That's basically why the integral of the second term is 0. Basically, the integral of S hat over the phi coordinate is 0. You see this dV. Now dV is equal to S ds dz times d phi. And integral of S hat over phi, this is 0. If you can write it in terms of its components, the components will be proportional to sine phi or cosine phi. You are integrating sine or cosine phi over a full period. So that's why that is 0. So the angular momentum per unit length is just minus sigma a I n pi b squared minus a squared in the z hat direction. Well, let's do a sanity check. You see, we had already seen that there is momentum is circling around the z-axis. Well, if the momentum is circling around the z-axis in the clockwise sense, then the corresponding angular momentum is into the screen. So that's why we ended up having an angular momentum in the minus z-hat direction. So at least it seems that directionally it makes sense.
Say we increase the current, then something should rotate in the opposite direction.
Let's see, I will cut the current. Okay. Now let's look at my system. This was my system. The current was running in this direction. Now as I change the current, I know that there will be induced electric fields. What will be the direction of this induced electric field as I is decreasing? Circular or counterclockwise or counterclockwise? You see, B field is outside. It will be counterclockwise, because if we put a wire there, there will be an induced current. The induced current should be such that it should increase the magnetic field out of the screen. So there will be this electric field inside. Induced electric field. Okay? Everywhere, at every point. But you see, here I have some charges, sigma. They will feel a force, so they will start rotating. But if they start rotating, they acquire the angular momentum. Well, basically the same thing will happen for the outer solenoid also. Well, we didn't put any charge on the outer solenoid though, so forget. If the outer solenoid, I mean, you can put the charge Q inside, charge minus Q outside, and then do the calculation. The outer solenoid will also rotate, so they will acquire the angular momentum. So as we change I, something will be rotating.
Could it be the charges in I themselves?
That will be rotating. Well, you see, the problem, okay, why I don't want to consider the outer solenoid in this problem is that, okay, what is decreasing the current? There are some external effects. So how do the external effects change the total angular momentum of your system? So without really describing that, I mean, it's hard to calculate the change in the total angular momentum and see that it's actually conserved.
So here we basically neglect the N to Q relation of the charge carrier.
No, we didn't neglect anything.
In the charge carrier, in the Y.
No, we are not neglecting them. Oh, you are saying that they also have angular momentum. Yes, and we are neglecting that angular momentum. The charge carriers have their momentum. So you see, let's see. Suppose I is decreasing. Initially, it has a large angular momentum in this direction. So as I is decreasing, it will have a smaller angular momentum in that direction. So the angular momentum in the electromagnetic field will increase in this direction. Right? But the inner cylinder will start rotating in the counterclockwise sense. So it will acquire an angular momentum in the same direction. So what's wrong? Or is something wrong? Anyway, that is for you to think. Any last minute questions? Well, the trick in identifying these conserved quantities is just to use the continuity equation. So that's the only thing we did. Of course, there are all these technical derivatives, vector equalities, etc., vector identities that we have to use. But once we can write our continuity equation, we are done. Okay, so see you on Friday.